Theoretical physics is a branch of physics that deals with the development of mathematical models and frameworks to explain and predict the behavior of the physical universe. Theoretical physicists use a variety of mathematical and conceptual tools to construct models and hypotheses that describe the fundamental laws of nature and the behavior of matter and energy at a wide range of scales, from the subatomic to the cosmological. Theoretical physicists often work in collaboration with experimental physicists, who perform experiments to test and validate their theories. Together, theoretical and experimental physicists work to advance our understanding of the fundamental laws of nature and to explore the mysteries of the universe. Without our understanding of the underlying mechanism of the nature, all kinds of today technology would be impossible. For examples, communication networking, global positioning system, GPS, high-performance computer and magnetic resonance imaging. The Institute for Fundamental Study, or IF in short, was officially inaugurated on March 14, 2011 by Naresuan University Council as a research center unit. From the first day to the present, IF members are working on the cutting-edge areas of research in theoretical physics to expand the boundaries of our understanding of the fundamental laws of nature, including cosmology, gravity, string theory, quantum information science and mathematical physics. We would like to emphasize that frontier research in theoretical physics is essential for advancing our understanding of the universe and developing new technologies that would benefit not only Thailand but the world society.
Okay, hello everyone. I'm very happy to introduce Avik here. So Avik has done his Ph.D. from University of Calcutta in India, and then Avik went on to do a postdoc in Malaysia, University of Malaya, and then he got a position at University Tunku Abdul Rahman, and he has been an assistant professor of mathematics where he is now based. So yeah, I give the stage to Avik, who will talk us about something interesting, a formulation of gravity that most of us probably not heard of. So I give the floor to Avik.
Thank you. Thank you, Soikat. Thank you. Okay. Thank you. Okay. So, thank you, everyone. The title of my talk is Gravity of the Connection. So, we want to discuss about gravitational theory, but we want to include the connections, FI connections, as an important part of it. So this is the abstract of the talk. In brief, we will explore what we are going to do today is to explore fundamental geometry concepts that are frequently overlooked while we immerse ourselves in advanced cosmological research. In the field of general relativity, we study the curvature of spacetime and often ignore the presence of the affine connection as an important player of this game. Because in the Einstein's theory, we actually have the connection inbuilt inside the metric. We can prove that gamma is a function of G, so we don't really take this into consideration. So what would be the outcome if the affine connection were to emerge from its height and produce a field equation of its own? This inquiry leads us to explore new theories of gravity. Particularly, we are going to discuss today about FQ theory. The Q stands for non-metricity, some concept non-metricity, which has gained favor due to its non-metricity-based nature. Okay, so I start from a very basic understanding of tensors, and then we gradually move into the differentiation and then the connections and all. So this might be well-known things. So if we have a vector space, we can have more than one basis. So if we have a bar system and an unbar system, so I just I repeatedly talk about a bar system and an unbar system. So this is one basis and this is another basis. So then there will be this kind of transformation law, EI bar to EI. So we can have a transformation A. So just keep in mind, we will use these few times after this. So when we have a unbar system and we want to go into the bar system, we use the matrix A. And we want to go to the unbar, we use the matrix B. Okay. So here, as well known, that B and A is the inverse of each other. So now, if we have a vector X inside that vector space B, suppose we name it B, the vector space. So if we have a vector X, we can write X in terms of the bar, unbar and bar both system, both bases. So suppose Xi is the component according to with respect to the EI, and if we have a E bar I, then the X bar is the components of Xi, or components of the vector X. So then we can write a relationship between the two components, the Xi without bar and the X bar I, which can be done very easily with these kind of things because of the linearly independence of EI. Okay? So from these two, we can see that if we want to go from the bar to unbar for the components of the vectors, we need the matrix A. It is not the same. It is opposite to what we are doing here. Here, when we are going from unbar to bar, we needed the matrix A. Okay, but when we consider the component of a vector in the vector space, we actually need the opposite. When we go from the bar system to unbar system, then we need the matrix A. Okay, and then vice versa. I mean, when we are going from the unbar to bar, then we need the matrix B. Okay, so this is some kind of contrast, some kind of opposite to what we are using for the basis. Okay. Contra, okay, the word is contra that we have to keep in mind, and we can define a dual vector space. Suppose V was the vector space that we are talking about with the scalar field F. Then we can define a dual space where the elements of the dual vector space are the linear transformations, linear functions over the vector space from the V to F. Okay, and there is this kind of operations, so that we can form a vector space. The dual vector space become a vector space. Okay. So anyway, we don't go into all these details. Just we have a vector space V last time, and now we are talking about all the linear functions from the V to F, and we call it a new vector space as V star, the dual space. So since we have basis in V, suppose EI is a basis like last time, then we can show that upper script I, EI, will be a basis of the dual vector space V star if the EI satisfy these. This is a linear transformation, EI operating on EJ, if it is a Kronecker delta Ij. So then the EI will be a basis. Okay. So that means since we have two different bases, a bar system, unbar system in the vector space. So in the vector space V star, we also have two different bases. Okay. So one is we define one by the bar, and the other is unbar. Okay, the EI and E bar I of V star. So we can show that this EI and E bar I will be related by these rules. Okay, I mean easy, but anyway, I just give the calculation. I think it's quite straightforward. We have there should be a bracket. There should be a bracket. So EI operating on EJ is delta Ij. So if the EI we change it in terms of bar, and also the EJ we change in terms of bar, then we easily get it. Okay, so C and B will be inverse of each other. So therefore we get this. Okay, therefore we get this. Okay, I think the proof is quite straightforward. So again, last time when we have the unbar to bar, we needed the matrix A, but here we are needing the opposite, the B. Okay, we need the opposite, the inverse matrix, the B matrix, to go from unbar to bar. So now next what we do, we just consider an element of V star. Okay, suppose there is a U, one form, we call it covectors or one form. Suppose U belongs to V star, dual space, and then U has the components UI in the unbar system and U bar I in the bar system. So according to the corresponding to the EI and E bar I, we have these two components, UI and UI bar. Then we can show that ui bar will be like this. Ui bar will be a j I uj, and ui will be b j I u bar j. Okay, the proof is given, but I mean easy, again quite straightforward proofs. So if we have u equals to ui ei and also u bar j ej, so this ui ei, the ei we can change it in terms of e bar j, then we can get this relation. Okay, so I'm not going into details of these proofs, but just look at this one. Now again, if we have from unbar system to bar system, we need the same matrix A. So it's the same thing like what we needed in the EI to EI, in the EI to EI bar in the original vector space. Okay, so that's something we say means similar kind of transformation. Okay, so that's one of the I mean justification, or maybe we can say some kind of reason we call it co-vectors and component of a vector space contra vector. Okay, contra variant. Okay, so this idea actually we can generalize, and then we can get the covariant tensor and contravariant tensor. Okay, so what we can do is, this one was linear functions, this V star was the collection of linear functions. So now if we generalize this to bilinear, means some kind of transformations from V star to W star, which is linear in both the components, like this and also like this. Okay, so if this one is AB1 star plus BB2 star, we can write this way. And also if in the second component we have AW1 star plus BW2 star, then also we can write in this way. Okay, so we call this bilinear, two times linear, you can say, okay, loosely speaking. So now if we consider a vector space containing this kind of bilinear functions, and operations, we can call this a tensor product, and we denote it by V tensor product W. Okay, so if EP, so this V tensor product W is formed using the V star and W star. So now we want to look at the basis of this V tensor product W. So we know that V star has a vector as a basis EP and also E bar P. Okay, so V star suppose is EP and W star suppose EQ. Then for this V tensor product W, we can always have a basis EPQ, which will satisfy EPQ operating on these two, giving us the Kronecker delta, delta IP and delta JQ. Then this will be a basis of the new vector space V star, V tensor W. So when we generalize the idea of from contravariant vector to contravariant tensor, what we do is, instead of taking only one vector space V, we just take the tensor product, suppose R0 order, then we take the tensor product R times, and we call this contravariant tensor. Similarly, a covariant tensor, instead of a covector, instead of a one form in the V star, element of V star, we can just take R times tensor product of V star, okay, the dual space. Then we will get covariant tensor. So similarly, when we define a mixed tensor of type RS, R contravariant and S covariant, then we can just think about an element from the V tensor product V R times and V star tensor product V star S times. Okay, we can call this a mixed tensor. Okay, just to give a bit of story, you can say. Okay, because otherwise most of the time when we discuss tensor, even in my undergraduate times, I remember when we first introduced to tensor, we just learn about something like this: is some mathematical entity which is invariant in change of coordinates. Okay, so we just define something like, if we have two different coordinate systems and then we have a, then this will be same. Then we call this a tensor. Okay, and then we always have some kind of transformation rule like this. So when we have this, we can denote it by a bar alpha in short, and then the a bar alpha become a covariant tensor. And similarly, we define the a contravariant alpha, so the superscript or upper script. So this one we call this the contravariant tensor or vector. Okay, this is actual vector. And the mixed tensor satisfy this kind of transformation law. So when we have alpha beta, we have a del x bar alpha del x bar beta, and when you have gamma delta, then the del x bar gamma del x bar delta will be in the denominator. Okay, so something like this. We usually just define the tensors this abstract way. So I just tried to give a bit of story about Vita contra and Vita co. Okay, so I think all these things are quite well known. So now our target is to define the connection. Okay, connection can be defined in many ways, like as an alternative of parallel transport and all those things. I go in a different way. I try to show that if we take a tensor, like a covariant tensor, suppose A bar S is follows this. So now suppose we want to do a differentiation of A bar S. We just take a differentiation. So del A bar del X bar K, if we do it, so there will be del AR del XP here and these things, but there will be another term which is del 2 XR del X bar K del X bar S AR. So this one actually a problematic term. This tells us that the partial derivative of a tensor is not a tensor anymore. It's not satisfy the same transformation law. Okay. So this tells us also that we need some other kind of differentiation. Partial differentiation is not enough. It's not a tensor anymore. So we define a new kind of differentiation. We call this covariant differentiation. Partial derivatives plus some, you can say, some correction term. I think this maybe is not a very standard term. We don't call the connection usually correction terms. I just try to introduce in this way, in a different way. So the partial derivative was not a tensor, so we add something and make it a new kind of differentiation which follows the tensorial law. Okay, so we add this correction term and call this a connection coefficient, which are not tensor themselves. Okay, so we have partial derivative which is not a tensor. We add another term which is also not a tensor. But interesting thing is when we add these two together, the total thing becomes a tensor. Okay, that's quite interesting. So when we take a covariant differentiation of a tensor, it transforms a tensor in arbitrary manifold. If we take A to be a PQ type tensor and then take a covariant derivative, A semicolon K, this is the usual notation, A semicolon K is derivative of A, covariant derivative of A at with respect to K. So then we will get a PQ plus 1 tensor. Okay, once we take the covariant derivative of A, it will be the suffix will be 1 increased by 1. And this covariant differentiation satisfies linearity and Leibniz rule. And it acts on scalars as a partial derivative, just simple partial derivative, okay, on a scalar. So this is the standard definition that we write. The delta K or nabla K Vi is the partial derivative del K Vi plus some extra term. This extra term is given by gamma, which is called the connection coefficients, gamma I K L V L. Okay, so there is a summation here. We use the summation convention, so we don't use the summation sign. But once we have the like the upper and lower, so there is a summation actually. Okay. So now the thing is, this is something we define for a covariant, for a contravariant vector. Sorry, for a contravariant vector. Vi contravariant, then we do the covariant derivative. We have this sort of laws. So how about the covariant differentiation of a covariant tensor or vector? Okay. So if we take AI to be a covariant vector and then we take a covariant derivative of this, then it should be del K AI, and as we said, there will be some kind of correction term, some extra term. Okay. So we don't know about what will be this connection, this term. So we just suppose write it as a gamma bar. Okay. We don't know what will be this, so we just write it as a gamma bar. Okay, we are still talking about the same covariant derivative. Okay, we just denote it by gamma bar, and then later we will try to find out what will be gamma bar. So maybe we just look at the proof here, the calculation. So suppose AI, this AI is a 0 1 and Vi is a 1 0. Okay, so covariant and contravariant. So if we take this becomes a scalar, and we take a partial derivative. Okay. So this partial derivative, like I said in here, the last one, the partial derivative will be same as covariant derivative when we act it on a scalar. Okay, so This partial derivative is same as the covariant derivative on the scalar, but the covariant derivative, we know it satisfies the Leibniz rule, so it will be nabla k ai vi plus nabla k vi ai. Now this nabla k ai, this is covariant, so we follow the gamma. Okay, sorry, the covariant is this one. Covariant, we follow the gamma bar, so we write as the gamma bar. And for this one, it is contravariant, so the previous page, so we follow the gamma, the usual gamma. Okay, so now you look at the first term del k ai vi and the third term del k vi ai. So together, these two together, we actually get back the left hand side. Right? This is the Leibniz rule. So del k ai vi will be del k ai then vi plus del k vi ai. So these two together, first term and third term, will give us the left hand side. So these two terms cancel out. Okay, these two terms cancel out. So we actually get gamma bar lki equals to minus of gamma I kl. That is what written here. Okay. Okay. We just, I mean, we need to, of course, we need to change some of the things like the this one is L and I. We need to just dummy index. We just need to change. So then we can get the gamma bar lki alvi plus gamma lki VIAL will be 0. So we get gamma bar equals to minus gamma. So that means what we obtain here is that when we take a covariant derivative, when we take a contravariant tensor, we get plus gamma, and when we use the same covariant derivative on a covariant tensor, then we get minus gamma here. Okay. So if we have a mixed tensor, nabla I t j k, we will have the del I t j k. First is the partial derivative as usual, and then the correction terms. So the correction terms, the first one corresponding to the covariant, the contravariant term j. So we have this, and then the second one corresponding to the covariant term k. So we have this with a minus sign. Okay, that will be the law for the covariant differentiation. Okay, okay. Maybe I. This may be, can I write here or that side? Yeah, okay? Okay. So we suppose trying to do this kind of things, nabla u of v. So two vectors, two tangent vectors. Then we can just write it as a u mu. This is like an axiomatic approach. So, and I write v as nu. Okay. So e nu. So this is the term actually, the nabla e mu, which will give you the gamma. Okay, this is the gamma. So we are used to with this kind of things. So I just tried to give a different perspective with like a correction term or some extra terms. Okay, from the partial derivatives. Okay? So same thing. This is just the component-wise calculation. Okay? So. Okay, so the connection is not uniquely defined in the sense this is like a correction term. So if we change the gamma, we will get a new kind of covariant differentiation. Okay, so the gamma is like a components. So gamma, alpha, beta, lambda is like few values. If we change that, we will get a new kind of covariant derivative. Okay. So this thing equivalently can be described, this whole thing, the covariant derivative and the connections can be equivalently described from the concept of parallel transport. Okay? So I just briefly go through this. Assume P and Q to be two adjacent points, and we wish to compare two vectors as the two different points. Okay? So the problem here is that if we have a point P in a manifold, if we have a point P and a point Q, so at point P, the tangent vectors are inside TPM and the Q is inside TQ, I mean the M is a manifold. So if we consider two different vectors, one is lying at point P and one is lying at point Q. So the, I think I gave it the name, any name? Okay, not yet. Okay, so anyway, so suppose U is at P and V is at Q, then they are lying into different spaces. So when we want to compare two vectors in P and Q, there is a difficulty because they are not in the same room. So we cannot simply compare the two vectors. So what we do, we just parallelly transport, we use this concept parallel transport so that there is a like a curve and we move the vector from here to here and then we compare the two vectors. Okay. So assume P and Q be two adjacent points and we wish to compare two vectors at these two different points. A parallel transport is basically a map P gamma, gamma is the curve, P gamma from S to T, suppose S to T, I just write gamma S to be the point P and gamma T to be the point Q. So I give it the name P gamma S to T, which is going from TPM to TQM, and it assists to transport a vector VP, okay, I give the name VP at the point P, along the curve gamma to a vector Q, name VQ, suppose, okay? Okay. So, given a connection gamma, I didn't show all these calculations, but given a connection gamma, it induces a notion of parallel transport P gamma, and also if we are given a parallel transport P gamma, we can find a connection, a particular connection gamma. Okay, there is a relation. Maybe I just for reference, I just write down here. Of the P gamma at the point S equals to 0, this will be gamma alpha nu. Okay, anyway, this one is not so important. But anyway, the important part is whenever we have a connection gamma, we have a parallel transport and vice versa. So the parallel transport and connection both are not unique. This is an important thing to remember, that they are not unique. So once we change the connection, we change the parallel transport. We also change the covariant derivative, okay, or the directional derivative. If we do a parallel transport and then this is the relation between the two vectors. If we do a parallel transport to a vector VP to VQ, we have a VP, we move it to VQ along the curve gamma, then we have this kind of relations. VQ, the component, VQ will be VP minus the connection is involved, the gamma connection is involved here, okay? So this, due to the existence of this connection gamma, which is not unique, there are few problems, okay? I don't. This is the tangent, the gamma. There is a tangent. We will name it U. Okay. Gamma, the curve gamma. Gamma. Okay. So, we are going to use this this relation. I will not show all the calculation, but we are going to use this to show that there are some unusual circumstances due to the existence of this connection gamma. Okay. So these are the three things: curvature, torsion, and non-metricity. Maybe I just okay. So there are three things: curvature, torsion, and non-metricity. These are quite significant in geometry. Okay, there are three geometrical entities, and all these three are related to the connection, or you can say related to the parallel transport. Usually, when we have the Euclidean geometry, when we have some vector, suppose U, and some vector V. Okay, maybe I don't. Okay, U and V. So there is suppose a point P and there is a point Q and point R. So we can always move this vector V along the U, and then we will get a vector here, pointing suppose at S. Okay, and then there is no difference between this vector and this vector. Similarly, we have a vector u here. We can just move it along this, and we can have like this. So this u vector goes here, and then again this and this has no difference. Okay, and okay, and then when we want to do the u plus v, we can write this is w. This w is just this w. Okay, maybe I write this one. Okay, that this concept is I mean, from the high school, from when we were a kid, we just doing this all the while. So we just move the vector at our wish on the plane anywhere. Okay, and then there is no change. So when we have something like this to this and this to this, there is no difference. Everything going to the same point S. Okay, going to the same point S. But this concept is true due to some specific kind of gamma and some specific kind of later we will discuss about the metric tensors. So this is not really true in general. Okay, because as you can see in the previous slide, when we move it, and if there is a gamma which is non-trivial, then when we move from here to here, it might go to somewhere here, and when we move from this u, from this point to this point, it might go to hit this point. So both of them might not reach at the same place anymore. Okay, or even if you take a vector from P, if you move this along a curve and the curve is closed, then if you move a vector, you move the vector like this, it might not go back to the same position anymore. Okay, the direction might not be same anymore. Okay, so these problems or these interesting phenomena are given by these three entities: the curvature, torsion, and non-metricity. Okay, so if we read the first one, curvature, parallel transporting a vector around a closed loop results in a change of direction for that vector. This change is measured by the curvature tensor R alpha beta gamma delta. Okay, gamma lambda. Okay, so I briefly I will write the things. So I just go through this one first. Torsion. What is torsion? Like I said, if we move this and if we move this, might not go back to the same position anymore. Okay, that difference is called the torsion tensor. If a vector Vp is parallel transported along UP up to its tip at point Q, it will not be same in general as parallel transporting UP along Vp up to its tip. That difference is measured by the torsion tensor T alpha beta lambda. Okay. Okay, I just believe me that they are tensor for the moment. Okay, because we should also later we should also check that they are actually tensor, the torsion, at least the torsion. Non-metricity, the last one. When a vector V is being parallel transported along a curve gamma, the magnitude norm V square changes from point to point along the curve. This change is measured. Okay, this change is measured by the non-metricity tensor Q alpha beta lambda. Okay, so this one maybe we can simply try to understand this in this way. We suppose I write Ft equals to norm of V square. Okay, V is a vector. Can you write as T? Anyway, just a parameter, just loosely speaking, Ft is a norm V square. So when we take a point P and point Q, this f function at the point P and at the point Q, it is not time, it's just roughly speaking. So at the point P and at the point Q, this should be Fp minus Fq. So the norm V square at this point and norm V square at this point. So this should be something like maybe I write P1 with a Q minus P, roughly. So when we have this term equals to 0, then only we always get the Fp equals to Fq. Okay, when we have the F prime to be 0, then only we are sure that we will always get the same values for F. Okay, here when we do the derivative later on, just later on, when we do a derivative like nabla x of G, the metric tensor, this is no more 0. This is no more 0, the non-metricity. Okay, instead this will be given by a new entity Q, okay, a tensor. We will show that this is a tensor. So because of these non-zero things, we will not get the magnitude always equals to, I mean the difference in the magnitude always equals to 0. Okay, roughly speaking. Okay, so I have few diagrams. I just try to draw here. Curvature. So suppose we start from a point P. And point S, and so this is a closed loop. Suppose there is a closed loop, and we have a VP here, and this VP, this vector, we are moving. So here we have a VQ, here we have a VS, here we have a VR, and then ultimately this will come back here. But because of that gamma, that equation, I will write down the equation. Because of that equation, it might not be the same VP anymore. It might be something like VP prime. Okay, so because of this, this one, because of this equation. So that difference, this VP prime and VP, that difference will be measured by the Riemann tensor R. Okay, so I just show you two steps. I think should be enough to understand the things. VQ nu, the one written in the slide. So mu lambda at the point P. So this is at the point P. So when we write a suffix, so this is point Q, this is point P, the same vector. And then the gamma, now we still measuring the P at the point P, delta U mu, and the V at the point P, lambda. Okay, so from here we move it to here. Now from here we have to move it to here. So we will have Vs equals to Vq nu Now this one we are considering from here to here. So we are calculating the things at the point Q. So I write a point Q. And we give it a name delta U, gamma U, and gamma W. So delta W is the tangent vector. Okay. So gamma U and gamma W. So this one is delta W mu V lambda at the point Q. So this VQ lambda, we have the expression from here, and this VQ lambda, we have the expression here, and this one at the point Q, we can use the mean value theorem or the Taylor's theorem to write it in terms of the point P. Okay, so it will be a bit lengthy, but then we can use some kind of approximation, like I think only delta W and delta U, only two of them, and then ignore the rest of the terms. So ultimately we will get something like this. Vs, I think Vs nu minus Vs nu prime, and this will be V this is nu. Okay, delta W nu. Okay, so that's why this tensor, the R alpha beta gamma delta, this is used to measure the difference between the two tensors, the difference between two same vectors in a different the parallel transported in a different position. Okay, so I just show you one portion, so it actually need few more steps. So we have to bring it from here to here, then to here, then we can find out the relation. Okay, but anyway, the thing is that geometrically curvature is measuring the difference between the same vector and when it is parallel transported from on a closed loop to the same point again. Okay, that is a curvature tensor. Okay, about the torsion, like I say, suppose we start from a point P and we go to Q. This is delta U and delta V. So this is delta UP and delta VP. So if we move this to here, this vector we move it to here. This point, suppose we just give it a name R. Okay. So then suppose this one will be here. The end point is S1. This is the delta U at the point R, and then when we move it to here, it may be somewhere here, S2, which is delta VQ, okay, and the difference between this and this will give you the torsion, okay. So I again use the same formula. So this is delta VQ, delta VP alpha minus gamma alpha mu nu. So this, if this is delta VQ, then like we usually do, W equals to U plus V. So I write down delta W at the point P will be delta U plus delta V, delta U and then delta VP. So delta UP alpha and delta VP alpha delta UP. But when we do the opposite, we give it a name delta W dash P alpha delta UP delta VP alpha minus gamma alpha mu nu P plus delta UP alpha mu. But when you do the opposite one, this one we move it. So we have now this one mu nu, so it will be delta, we are moving the V, so VP mu UP nu. Okay, so this one is delta UP mu delta VP nu. So if we want to write it as a delta UP mu and delta VP nu, we have to change the mu nu. Okay, like dummy index. Okay, so I just change the mu and mu to be nu here, and the nu we change it to mu. Okay, so now we write the alpha and delta WP. So these two terms are same. So it will be So it will be this is minus, so gamma alpha mu nu minus gamma alpha mu nu. Okay, and then the delta u and delta v. Okay, so this thing we call it T of alpha mu nu, the torsion. Okay, this is called torsion. Okay, so that's why we say the torsion is actually measuring the difference between the end points. Okay, when we move it from this to this and this to this, the difference is measured by the torsion. Okay, the last one is the non-metricity. So non-metricity is giving us the measurement of the difference. Okay, so suppose V is a vector, so norm of V is given by G mu nu, V mu nu, V mu and V nu. Okay, so this is a metric tensor. As we know, this is a metric tensor. So norm V square is given by the G mu nu, V mu, V nu. Okay, so and the V is this V vector. We consider the V vector is parallelly transported along some curve gamma. Okay, and then U is the tangent vector. Okay, U is the tangent vector. So that we will have nabla u v equals to 0. Okay, or maybe we write it in the component wise, because the same thing we just write as u alpha u mu. Okay, anything u alpha nabla alpha v mu equals to 0. Same thing, equivalent thing we write as a component. Okay, so when we measure the difference, like I just now discussed, when we have a f of q, f of p, the main difference is the f dash at some point. Okay, so if we measure that difference, it will be u alpha nabla alpha g mu v mu v nu. So we use the Leibniz rule, this one operating on this. This is v mu v nu plus this is nabla alpha v mu v nu, left it, and then v mu nabla alpha v nu. Okay, so if you look at the second term and the third term, you can actually change the mu and nu here. These are dummy index, and then g mu nu is symmetric, so g mu nu is g nu mu. Okay, symmetric. The metric tensor is symmetric. So if we just change this dummy index, you write this as a nu and this one as mu, there is no change. So this and this actually are the same element. Okay, same terms. So we can just write twice this and we just ignore the third term. Okay, and then this nabla alpha v mu, this part is equals to 0. Okay, so this one actually gone. So we actually get u alpha nabla alpha. Maybe I write this one first. We write nabla alpha g mu nu, and the rest of the terms are u alpha v mu v nu. So this one is actually denoted by q alpha mu nu. the non-metricity tensor. Okay, this is called the non-metricity tensor. So that's why we say the non-metricity tensor is actually measuring the difference between the magnitude of a same vector in two different parallelly transported planes. Okay, so these are the three things. Okay, now the connection, like I said, the partial derivative of a tensor is not a tensor. The connection itself is not a tensor. The connection itself is not a tensor. But you see that if we consider two different connections, gamma and gamma bar, corresponding to nabla and nabla bar, we just consider two different. It is this. Okay, this. So if we consider gamma is one connection, gamma bar is another connection, then corresponding to this, we can define a covariant derivative nabla, and corresponding to this, we can define a nabla bar. So this is not a tensor, this one is not a tensor, but we can prove that if we take a difference between two connections, that will be a tensor. Okay? So if you take nabla k, vi is any vector, any contravariant vector. If you take nabla k vi minus nabla k bar vi, if you take nabla k vi minus nabla k bar vi, so this is one tensor. Okay, the covariant derivative is a tensor, we know. This is another covariant derivative of the tensor, so this is also a tensor. So left hand side is a tensor. Now if we write down nabla k vi, it will be del k vi plus gamma ikl vl. If we write down nabla bar k vi, the definition is del k, the partial derivative, plus, so this one minus, so there is a minus, gamma bar ikl vl. So if you look at this one, this is delta k vi cancel out, so you only get gamma ikl minus gamma bar ikl multiplied by vl. Keep in mind vl is also a tensor. Okay, so in tensor calculus we have a law, we call it quotient law. Quotient law, which says that if we have something like A multiplied by B equals to C, and we know that this is a tensor and one of them is a tensor, suppose A is a tensor, if we know, then B must be a tensor. Okay, so if we have two different things, two things, and we multiply, the product is a tensor and one of them is a tensor, then the second one must be a tensor. So that means if we look at here, we have the left hand side a tensor, VL is a tensor, and the multiplication is by this. So this must be a tensor. Okay, so the difference between two connection coefficients are always a tensor, although the connections coefficients are not a tensor. So forget about this one. Suppose we have a gamma. So we have the gamma A, B, C and corresponding covariant derivative. Okay, and suppose we think about a new connection. Just call it a new connection, gamma tilde. How we define this? So we know that gamma ABC equals to whatever. So gamma 0, 0, we know, gamma 0, 0, 1, we know, and so on. So if we define a new connection and a new covariant derivative, just by writing this ABC equals to gamma ACB, we can do that. We can always do that. So it's just gamma 0, 0, 1. If it is 1, so gamma 0, 1, 0 will be this one. Okay, so we can, gamma bar. Okay, so we can consider that gamma ABC is one connection and gamma ACB is another connection. So the difference, this minus this, must be a tensor. That's why the torsion is a tensor. Okay, the torsion TIJK, the torsion TIJK equals to gamma ijk minus gamma ikj. This is always a tensor. Okay, so it's interesting in the sense sometimes we are a bit worried that gamma is not a tensor, gamma is a connection, it's not a tensor. Then how come the T is a tensor? Okay, so this is the reason. Okay, the difference is a tensor. Okay, the metric tensor, as we know, if we have a dA square equals to the x1, x2, x3, these things are the coordinate, and then we can write ds square equals to minus dx1 square or something like this. Then the gij, ds square equals to gij dxi dsj. This gij is called the metric tensor. We can also define an inverse metric, and we can use this to lower or upper the index of a tensor. Okay, so we can always have, if we have a alpha, we can write it as g alpha beta a beta. Okay, we can always do this. Okay, so this is a very handy thing when we discuss the general relativity. So now there will be a problem, because when we take the covariant derivative of this, like a nabla mu of a alpha, there will be a bit of trouble. Okay, so when we discuss connections, at least in the general relativity, we actually always discuss only a particular very special type of connection, which is called a Levi-Civita connection, or sometimes we call this a Cristobal symbol. This Levi-Civita connection, this is a very nice connection. It's not an arbitrary connection. It's a very nice, unique connection which has two interesting properties. Okay, or we can say we define the Levi-Civita connection. We define Levi-Civita connection as a connection which always has two properties. Okay, the first property is the torsion, corresponding torsion is 0. So gamma ABC is always gamma ACB. So when we know the one of the triangle, the components, then the other ones already known. Okay, it's a very particular type. The gamma ABC is gamma ACB. And the second one is, it is called metric compatible. That means when we take nabla A, G, B, C, this is 0. Okay, this means the gamma. Okay, the gamma thing. So the whole thing will be 0. Okay, so we have these two particular property of the Levi-Civita connection. So Levi-Civita connection is a unique connection with these two. Okay, there is no other connection which has these two properties. Okay, so because of these two properties, we can actually write the gamma, this particular one, maybe I give it a name, give it a new notation, write by circle, math circle. Okay, so because of these two properties, the gamma naught can be written as a function of the metric tensor G, because of these two properties, okay, which is shown here. So suppose, very simple, we just write nabla I gjk. So nabla I gjk will be 0 because of the second property. So nabla I gjk, now we use the covariant derivative definition. So we have a partial derivative minus gamma Lij glk minus gamma Lik gjl. Now we cyclically rotate the ijk. So we have I changed by j changed by k, and k changed by I. Okay, and then this is metric tensor is symmetric, so I just write, instead of ki, I write ik. And I do it one more time, so j becomes k, I becomes j, k becomes I. So we have total 3 equations. Okay, and then if you take one of them and subtract the other two from it, you will get back this. Okay, you just take one and then you subtract this and this. So you will see there is a Lij glk, Lij glk. This will be cancelled out. Again, we have a Lkj gil, Lkj gil. So this will be cancelled out. Okay, so by 1 minus 2 minus 3, you will get back this equation. Okay, here we also use one more thing, the first one. So what I said here is that gamma Ljk is same as gamma Lkj. This is also used. That's why we get such a nice expression of the Levi-Civita connection. Okay, so Einstein theory is based on this particular Levi-Civita connection. So whenever we take a covariant derivative in general relativity, whenever we use general relativity, we use the metric tensor G. So there will be certain coordinate system, and we have the metric tensor G, and we have the gamma, which has these two particular properties. So we have a gamma mass circle. Okay, So the gamma mass circle is a function of G. Whenever we know G, we know the gamma naught. Okay, straightforward. Just a covariant, just a partial derivative, we get the gamma naught. So whenever we do a covariant derivative in general relativity, whenever we do a covariant derivative of any vector like a nabla x, y, this is actually corresponding to this particular connection. This is always corresponding to this particular connection. Okay. So we know this. So we know this always. Okay. Sorry. So Einstein theory, like we know, we have this. So the building blocks, like I said. Okay. Okay. Now we want to do a modification of general relativity by changing the geometry. Okay. We know that there are many reasons and many ways to why we modify and how we modify the theory of general relativity. So I just do some specific one by changing the geometry. How we change the geometry? We just consider that if we have the M manifold, we have the G, the metric tensor, and of course, whenever we have G, we already have a gamma naught. This comes together, okay, in a couple, okay. Not couple. I shouldn't use the word couple, but I mean this one comes with a bundle, okay, G and gamma naught. And now we are going to use a general affine connection gamma, which is not gamma naught. So last time we had a covariant derivative like this, which was very nice. Now we have a new covariant derivative, which is not so nice. In the sense, when we do a nabla naught of G, this one was 0, but now we have some kind of things, non-zero things. Okay, and also last time when we have a T, I mean when we have a gamma ABC was gamma ACB. Now no more. Okay, may not be same. Okay, so depending on this, we can have few kind of theories. Okay, if we take the non-metricity to be 0, the torsion 0, curvature 0, we can get back the special relativity. For general relativity, we have non-metricity 0 and torsion 0, but the curvature non-zero. So we use the curvature for the gravity. Similarly, in teleparallel, we should say metric teleparallel gravity. The non-metricity is 0, but the torsion is used for the gravitation. And the symmetric teleparallel, where the non-metricity is non-zero, but the rest of the things are 0. Okay. So I just look into the torsionless, curvatureless geometry. Okay. So I saw this part. Okay, this one. So this one, if you look at this, nabla I, G, J, K, this expression and cyclically writing these things, when we consider that our nabla is this nabla, not the Levi-Civita. This nabla, the covariant derivative, is a general one. That means the left hand side we will have Q, I, J, K. Right? Similarly, the second one will be Q, J, K, I. And we have Q, K, I, J in the left hand side. So we do the same thing. We again repeat the same thing. We have one of them, subtract the other two. Suppose the first one, then we take minus the number 2 and number 3. But then the left hand side will have Q, I, J, K minus Q, J, K, I minus Q, K, I, J. Not 0. Not 0 anymore. Okay, we have these terms. And also, last time we cancel out like this gamma L I J, gamma L J K and gamma L K J, we actually cancel last time because this one was torsionless, this one was symmetric. So gamma L J K and gamma L K J was same for the Levi-Civita, but not anymore. Now we don't have this property anymore. So when we take this minus this minus this, there will be some extra term which will be given by the torsion T, right? Right? We don't have the things cancel out, so we have a T, tensor T instead. It will be T L J K G I L. For the last two terms, it will be T L J K G I L, like that. So if we do the same thing again one more time, we will get back similar thing like this. Okay. So the left hand side is like this. I think I take a minus sign, so this is 2 positive and 1 negative. But it's a I mean, straightforward. We just do the same thing again, and then we take into account that some of the terms are not cancelled out, but will give us the torsion tensor. So we get this equation. Okay, and then what we do? We just write these Q tensors, this Q, the non-metricity tensors, together, and we give it a name. For simplicity, we give it a name. And then we take the T tensors, the T here, we keep it in one bracket and give it a name. Okay, suppose we write this Q alpha beta gamma Q, this one, as a tensor L, and all these tensor, torsion tensor T, we gave it a name K. So that means from this actually we can get something like this. Okay, the gamma naught is the previous gamma naught. This gamma naught is the previous, the Levi beta gamma naught. So the gamma here, we only have gamma here. Huh? We only have gamma here. So this gamma will be, from here you get the gamma naught, from here you get the L, from here you get the K. So we get this expression. So any affine connection, general affine connection, gamma can be written as gamma naught plus something like this. Okay, we just give it a name. This is just a name. So this corresponding to all the non-metricity tensors, this corresponding to this corresponding to all the non-metricity tensors, and this corresponds to all the torsion tensors. Okay, so when we discuss our theory, there are some tensorial calculations. Just write down. These are useful. So actually. This is the connection gamma, this is the connection gamma naught. So from this connection gamma, we can find out the corresponding Riemann tensor. Corresponding to this gamma naught, we can find out the corresponding Riemannian tensor. So we will have a relation between the R and R naught. When we contract them, we will get a relation between the Ricci tensor, corresponding Ricci tensor here, corresponding Ricci tensor here. Okay, so we get such nice relation. Okay, we get such nice relation Rijkl, Rjk. Okay, the relation, and also we will get another time we will get a relation between the scalar curvature, the scalar Ricci scalar, the R and equals to R naught plus something. Okay, this is actually used. So you might know yesterday we were talking about the Zhao's paper, the covariant formulation. This paper we actually have done already, but we couldn't publish. This is the thing that they used. Very simple. It's just this one they used to find out the covariant formulation. We already had these calculations previously, but unfortunately we couldn't publish. Okay, so because the Ricci tensor is symmetric, and we also have the L. This is the L. We get it from here. Huh? The L is from here. L is from here. This L tensor is also symmetric in the last two indices. So we can see that from here, we can see that if we write down a Rkj, it will be, all the terms will be same. Just the nabla k qj will be nabla j qk. So we have this kind of things. Okay, we have this kind of things. Nabla j naught qk equals to nabla naught k qj. And from here, because of the relation between the gamma and gamma naught, so we have also a relation between nabla and nabla naught, as you can understand. So using that nabla naught qk, nabla j qk equals to nabla naught k qj, we also can get this relation. Okay. So far this one is not used anywhere. I didn't see this result is used in any of the papers. So it's a result which we should look into. I mean, we didn't really apply this finding so far. So anyway. So this is the scalar, the Ricci scalar, the relation R equals to R naught plus this. So now when we consider a new gravity theory without the curvature but with torsion or non-metricity, or maybe both, I am studying only non-metricity part without using the torsion. So the first thing is we don't have the R, the Ricci, the Riemann tensor is 0, the curvature is vanishing. So that means the R in the left hand side is not there. The R is not there. So that means in the absence of R, we have a relation between the R naught and the Q. This is R naught. There is this is actually I didn't write. Sorry. So actually we have a scalar Q, which is okay, and this expression is actually given here. Okay, this expression is this whole thing. So this is the Q. So R naught and Q are given by R naught equals to Q plus divergence of Q tilde L minus QL. Okay, so that's why we can write the R naught equals to Q plus some kind of B or C, some boundary term. Okay, some use B, some use C. Okay, B or C, whatever. Okay, boundary term. So when we consider the new theory, new gravity theory, like Einstein-Hilbert action, only thing is we replace the R or R naught by Q, we will get the same theory again. We will get back the GR because of the boundary term. R naught is actually given, Q will actually give us the same general relativity. But when we change it to F, like a FR theory, instead of FR theory, when we use FQ theory, there will be some other things. There will be some other new things. Okay. One second. Q. Yeah, same. So actually, everything is coming from L. This one. So in our theory, I mean, in my theory, what I am studying, we are not discussing the torsion. We consider torsion is also 0. To make it simple, we have only one thing. It's the gamma equals to gamma naught plus the L. The L corresponds to the non-metricity only. So from this L tensor, we can actually write a tensor Q. We can also write a tensor PABC. Okay, but it's just a name. It's just a name. I can say it's just a name. We just consider L and can formulate the whole theory. We don't really need this kind of things. We just take a Q. We just take the L. We do some kind of action term. We vary the thing. We can get back the FQ theory. Okay, so these are mostly some new names, you can say, the PABC and QABC, which actually is very helpful. If we use programming, then we just find out this tensor, and then just run it, and then we get back the Q, the scalar. Okay, so if we have we have two types. One is the metric teleparallel, one is the symmetric teleparallel. The metric teleparallel, we consider the non-metricity gone, the curvature gone. It's only the torsion tensor which is taking care of everything. So the whole gravity thing. So then we have this kind of things. Gravity is effect of torsion, and then gamma bar ijk minus gamma bar ijk equals to k. This is the contortion, and then t equals to, I think this one is t. This one is t, not k. I think this one is t. Okay. Then we can find out torsion scalar, like here, the non-metricity scalar. We can also find out the torsion scalar, and then we can prove the similar thing, the T gravity. I mean, if we replace the R naught by T in the Einstein-Hilbert action, it will give us the same GR. Okay, no new thing. But when we change from the FR, this R we replace by T. So if we consider the FT gravity, we will get some new things. And then the field equation will be something like the G mu nu plus some extra terms equals to KT mu nu. Okay. And of course, there are like all modified theory. I think there is some issues, some problems, which say good and bad tetrad problems. Symmetric teleparallel gravity is similar. We consider the K is gone. There is no torsion, no curvature. We only have gravity as an effect of non-metricity. Then we have gamma bar ijk minus gamma bar I. This is, oh, okay. I think I didn't use the knot in the slide. This one is the knot. Okay, the math circle. Okay, so we can define some new tensors Lijk, and then using this we can define the Q. Okay, but usually I think this is more popular. We just use this Q equals to QABC PABC. Okay? Same thing. I mean, same formula. We just have different expressions. Okay, So this Q gravity, again, Q, like I said, Q gravity is equivalent to GR, but when we take FQ, it's giving us some new things like FLRW. So there we have field equation like this, and we have some issue again, something which is called coincident gauge coordinates. We have good and bad coordinates problem. Okay, so which we are still discussing. Okay, so for the FQ theory, we have this field equation. So the E mu nu, I mean, forget about E mu nu. This is the left hand side equals to kappa T mu nu. I write it as theta because there is the torsion is we discussed by theta. So T, so I write theta. So this is our usual T mu nu. Okay, and then here the new thing is there is another field equation. So when we vary, when we have a S, the action term, we can vary it. We have an action term, we can, maybe I write in this form. This is a function of G as well as the gamma, the affine connection gamma. So when we vary it with respect to G, we get the first field equation. When we vary it with respect to gamma, we get the second field equation. Okay. So these are the two field equations. This is the with respect to metric. So we call it metric field equation, and this is the connection field equation. And then we can consider the divergence, the nabla naught mu of the metric field equation. Then we see that this can be written in this form. So coincident gauge.
No, there is no.
No hypermomentum. No hypermomentum. Yeah, I mean, I actually didn't. I mean, when we consider the SM, this is just G. Okay, it's not. SM is not a function of the connection. Okay, for simplicity, we just assume this one. Okay? Otherwise there will be a plus H mu nu type thing in the second field equation, in the connection field equation number 2. So we just consider that part is not there. Okay, the H mu nu is not there. So because in it. I don't know the actual reason, but this assumption is useful in a way that if the hypermomentum tensor we don't consider, then the energy conservation can be shown as equivalent to the connection field equation. I write it as Fe1 and Fe2. This is corresponding to the G, and this is corresponding to the gamma. So Fe1 and Fe2. So we can show that if this SM, the matter Lagrangian, is not a function of gamma, then the energy conservation and the Fe2 are actually equivalent. So maybe because of this, we assume this in most of the non-metricity based theory or the torsion based theory. Okay. Okay, and then I think I just stopped here for the FQ theory. I didn't go into actual results and all. There are few issues yet to solve. The one thing is in the cosmological background. How much time I have? Or I should stop? Yeah, I mean, I can stop here. I can just stop here. So yeah, I think I just stop. I just stop here. So, okay, one interesting thing, just last slide, my last slide. In differential geometry, we have this kind of things, semi-symmetric connections. Semi-symmetric connections. So these kind of connections can be metric connection, can be non-metric connections. So semi-symmetric means it's not really the Levi-Civita. It's Levi-Civita plus something. So this gamma bar, this gamma is a Levi-Civita connection. This is the new connection that we study, gamma bar equals to gamma plus some extra terms. These extra terms actually can vary. Like I have given semi-symmetric metric connection, non-metric connection, and metric parallel connection. So these kind of things, these concepts we had a long time ago. I think Kentaro-Yano time. Kentaro-Yano. he should be the first to discuss all these things. And then we still study this, but only in the context of differential geometry. So we have a manifold and we have a submanifold, and then most of the time is like what will be the Ricci the Ricci equation, Gauss equation, and all these kind of things. The differential geometry. We study these things. I also studied this before my. I mean, maybe I just let's continue like this. So I believe using this kind of connections, using this kind of connections, we can also define a new kind of gravity theory, like this semi-symmetric metric connection. We use this connection and then we just vary the case with respect to such a connection. We will get something. Okay, but I never tried this. I never tried this before. But there are other people who tried. This is. I think it's okay. I just last time. Thank you. So this is a one paper. I did this paper. This is one try. I think the first try in the semi-symmetric connection formalism for unification of gravity and electromagnetism. So this guy actually he used the semi-symmetric connection and then he derived the field equation, but not really cosmological application or anything. Not even the static spherical symmetry. Nothing actually. And then this is the new paper. I didn't read it. This is the new paper by Harpo. So this must be, I mean, quite into the cosmology and all stuff. It's the same thing, semi-symmetric metric gravity from the Feynman-Southern geometry with torsion to dynamical dark energy models. So forget about all these things. This actually is just the same thing as they say. They use the semi-symmetric connection and then they vary and then they take the geometry. So I guess this paper has all the cosmological applications. So I think these things has potential, or all these things, many more things in the which are hidden in the differential geometry. I think has potential to in future to be described in kind of theory. Like even this non-metricity theory is not as a form of gravity theory, but it is quite well known, and all these, like I showed the calculations, like Adolf's paper, there was one professor from Turkey, he has all the calculations. And then even before that, there are some papers who actually discuss all these things, but not in the context of cosmology or black hole theory or unknown theory. So nobody noticed those things. It's just again in the differential geometry. Same thing like this. SSMC, this one is maybe even before I was born. This one was studied, but now it's just this year. I just noticed this in 2024. They have this. This one also not very. This is just 2019. They discussed the semi-symmetric connection in the context of gravity theory. So this maybe have in future maybe have some new theories of gravity. Okay, I stop here. Thank you.
Okay, so everyone can ask questions if you have.
In non-metricity formulation, in non-metricity formulation, the connection in the definition of covariability is a non-metricity connection, or also includes the Levi-Civita connection. Yes. The connection is in the definition of covariability. Sorry.
The connection in the definition of covariant derivative.
Is a Levi-Civita connection, or is it the connection in the definition of covariability is not a compatible metric, right? It's not only this part, right? So this means that in the geodesic equation, the connection in the geodesic equation is also not compatible. Yes, but okay. Now we consider the action. If suppose that we have the matter action, and then we to obtain the energy momentum tensor of the matter, we have to vary the action with respect to metric tensor, right? Yes, and okay, the covariability in the equation for the conservation of energy momentum tensor.
It's a previous one. So in this one, P mu, when we do the energy conservation, we still use the Nagla
Levisovita. Yes, but so I feel that there are some conflict because in geodesic equation you use not computable connection, but in a conservation of energy momentum tensor you use the Levisovita connection.
Maybe the reason is this. So even in the F2 theory, we can write G mu with respect to the Levisovita.
Capital G mu.
The capital G, the Einstein tensor, with respect to the Levisovita connection, equals to the P mu and plus some extra term, some delta. So when you take the nabla mu, the covalent derivative of the Einstein tensor, if we take it with respect to the Levisovita connection, then this part is 0. So that's how we can get this nabla naught of T mu nu equals to 0, the energy conservation. I think there is one paper who actually considered both nabla with respect to the new connection, nabla mu T mu nu, and also the Levisovita. I can't recall which paper. By Koivisto, there was one paper. They considered both of them, and then they said for the energy conservation we must consider this nabla naught mu T mu nu, because there are two different connections. We don't say the curvature varies for the. I mean, we take a manifold, we take a metric tensor. We have gamma naught and we have gamma. We are not saying that corresponding to gamma naught, the demand tensor R naught is 0. We are not saying this. We are not saying that R naught is 0. So when we are discussing the non-metricity theories, we don't really disturb what we have in the Einstein theory. We are not saying anything about them. We are saying that we can actually also define the theories using a new kind of connection, which has no demand tensor, which has vanishing demand tensor, but has non-metricity tensor. So we are not disturbing the gamma naught, the Levisovita connection at all. So the energy conservation, we have to follow the previous whatever we have done so far in general relativity, in the classical theories. So we just follow the same lambda naught at the Levisovita.
Okay. I will discuss later. Okay.
I try to find out this paper. I know this paper, so I try to give you more information about the thing.
Okay. Next question. The last question. Is the independent variable of the Rahman tensor in the Einstein cavity same as the independent variable in the non-metricity tensor? Is the same or different?
The Rahman tensor
in Einstein cavity and independent variable in the non-metricity tensor. I mean Q alpha beta gamma.
You mean the number of independent variables?
Independent variable in two type of tensor.
I mean, what do you mean by the? What do you mean by the independent variables?
Degrees of
for example, because for example the metric tensor is a rank 2 tensor, right? And metric tensor is a symmetric. So there are 10 independent variables.
Oh, I see. Okay. So you mean G alpha beta, although there should be like alpha can run for 4 times, so beta can run for 4 times, so 16. It's actually alpha beta is beta alpha, that part. Yeah. So now we are talking about the Rahman tensor. So this Rahman tensor is still corresponding to the Levisovita, is still the same. So it still has the same symmetric properties and same identities.
Yes, but how many degree freedom Q in a non-metricity tensor? I mean, because there are three units for Q. Q is a naba mu G of
Oh,
G.
I see, I see, I see.
Yes, yes.
I mean, the Q, if we consider the non-metricity tensor Q alpha beta gamma. I have to check. I have written somewhere. I think beta and gamma is, of course, this is symmetry, beta gamma. So the last two index is symmetric. So I actually found how many.
Do you have to count the?
I have in my paper. I will show you. I will give you later.
Okay.
It's easy. I mean, this can run for 4 times, 4 times, and 4 times. So for this one, we have. I'll give you in 5 minutes.
Okay. Because actually, I would like to know how many degree freedom in FQ theory compared with GR. Okay.
Probably a simple question. Can you write down or give me like the equivalent Einstein field theory but in the Q formalism?
Yes, we can. I think we have. Can I? Most probably I have the last. This one. So you see the number one. So let's just ignore the E mu nu. Ignore the E mu nu. This is just a name I gave. Just forget this. So just forget this. So FQ G naught mu nu. This is the Einstein tensor. So Einstein one is just G naught mu nu equal to kappa E mu nu. So my one will have FQ G naught mu nu plus some terms as you can see, some terms like half G mu nu FQ Q minus A plus 2 SQ Q P lambda mu nu lambda Q. So this is the extra terms equals to kappa T mu nu. Okay, the theta I wrote here is because that time I was discussing the constant tensor also. So we cannot write the T, there is a confusion. So
For GR, you have to put F equals to Q.
Yeah.
So basically the same equation.
Yeah. So if we use FQ equals to Q, we get back the same as in GR. I discussed this here. You see the Q gravity. So when we replace the Einstein-Hilbert action, when we replace R naught by Q, we get back the same thing. But if we take an arbitrary function FQ, then we get something new. So I think this one is the theta is a bit. This is not theta. This is the T. That's just energy momentum tensor.
Okay. Because I remind that you said that you can replace R with Q.
Then we get the GR.
I'm not sure, but I mean we can replace R with Q, which is equivalent at the classical level, except for the boundary term.
Right. Except for that?
Except for the boundary term.
No, I mean, yeah. So we have Q equals to R naught plus C. So in Einstein-Hilbert action, so when we have one minus G and all, so we have I. Okay? And before it. So this R naught is giving us the GR, the general relativity. So if we replace the R naught and we write Q, I mean Q or Q plus C is same thing because C is a total derivative, so it will be one. So if we write Q, then we get like same thing again, general relativity. So only if we write instead of Q, if we write some other kind of functions of Q, then only we get some new theories. So that is the F here, FQ. So if we put FQ equals to Q here, then we just cancel out everything. We just get back G naught mu equals to.
Okay. So the R naught is a Dichy scalar.
Yeah,
right?
corresponding to the Einstein, the Leibniz connection. So because we have two different, because we have the gamma naught, the circle and gamma. So I just write corresponding to this. I write R naught, and corresponding to gamma, we have R equals to 0. Corresponding to the new connection, we consider this curvature less, so R is 0, so there is no R. So we only have R naught, the previous R naught.
Okay, thank you. And there is not in chain if we add like cosmological term, right? Because it's coupled to the the metric. So it that much you can add it into different theories.
Yeah. You mean the lambda, the cosmological
yes,
lambda.
yes.
So I think if we just take this as a q plus 2 lambda or lambda anyway, then we can get it.
Okay, I have two questions. One is, so this equivalent between Q gravity and R naught gravity is valid only when boundary terms are not important. Like I think in gravitational physics, sometimes boundary terms are important. I think in black hole theory or something.
Okay.
Yeah, so
if I mean, you mean if you write Q plus C or Q minus C, this is not called equivalent.
Yeah, it's equivalent only when you can make the boundary terms vanish. So, like we usually make the boundary terms vanish, the total derivative terms vanish because we integrate by parts and we see that they decay very quickly at the boundary.
So why we cannot do that? When we cannot do that? I mean, this one is a total divergence term. The C is total divergence.
Yes, but I know. I mean, I can vaguely recall in some areas in physics where we can, like this boundary term
should not be in
important.
black hole. Should not be in black hole.
Is it in black hole? Do you remember where?
Because I think in black hole they still study this.
Like why did Gibbons and Hawking's introduce the boundary term?
GHY term.
Yes. I mean, there must be some motivation.
I don't really know.
Yeah, but maybe just manifold with boundary. But maybe just random manifold with boundary. So should be worried about the boundary.
There may be some physical motivation.
Yeah. There is some physical things.
I don't remember now. But
I mean, when I started studying the GR, I actually tried to understand this GHY things, the calculations, because it's more towards geometry that time. But I don't really know the physical things, nothing at all. Because now this corresponding to this boundary term, we have this new theory, exclusive theory. I really want to know that GHY whether there is some relation between the C and the Gibbons Hawking York boundary term and it's the C. Can we discuss? Can we study more things in more depth?
Okay, and another.
I don't know.
Okay. Second question is, so GR is basically has two assumptions on the arbitrary connection. One is the connection is yes. So one is basically torsion vanish and it's metric compatible. And in non-metricity formulation of GR, you have two assumptions. Why? I mean, how can we be sure that we can always have two assumptions? Like how can you be sure that we can always take any two assumptions and make any two things vanish?
How can we
be sure that in any formulation of GR, any formulation of general relativity, we can make two things vanish? Like, is it, where does it come from? It could have been that we can only have the freedom to make one thing vanish.
You can do that.
We can do that.
I mean, technically, we can always do that.
like we can
No.
have
1 second. Like this? You mean this kind of things? Two things non-zero. This and this one non-zero, and only Ti 0, or maybe this one and this one non-zero, only this one 0.
we can still get a theory that is equivalent to GR.
I'm not so sure. I never really studied, but these things are not what you say like phenomenologically not important. These things are also studied in that cantata work or somewhere they discuss, but they say this is not really physically important.
But can this
Can be studied?
I don't
really
be studied.
study
I'm
this.
saying this. We
Can you get back a GR?
Can it?
Get back a
Yeah,
GR?
give
I don't
that
really know.
GR.
I never studied this one.
Because GR has an assumption. GR has two assumptions. They have only one assumption. So, can these
not so sure.
approaches give back GR?
I'm not so
Not sure.
Not so sure. Might be possible, but I'm not so sure. Might be possible. But it's just, I think, for now, I think it's not really better than GR or something like that. It's maybe just a different approach to it.
It seems not quite symmetric. I mean, what about another theory with like I'm not sure, but with T equal, I mean,
Zero?
like R equals 0, but Q and T not equal 0.
R equals to 0 and?
Yeah, we have like Einstein Y, Einstein Cartan, but I mean, should we have another kind of thing like R equals 0 or like
I
Q
see. I mean,
and T
Q
not
and T 0 and R non 0.
yeah.
Oh,
Is there actually such a theory?
I don't know. I don't really know. I mean, like technically, we can always have some kind of connection, and we can define a new thing. But whether it's physically is reasonable or not, I don't really know. I don't know. I mean, whatever we do here, we can always get some kind of relation like this: the gamma equals to gamma naught plus. That is always possible. The gamma equals to gamma naught plus 1 tensor will be 8. So this is always possible. So once we have this, we can always write R equals to R naught something. This is always possible. Mathematically possible, but physically, I don't know.
Okay. Okay. So thank you very much, Avik, for this nice exposition to something we thought we knew GR, but we never really thought that there can be other ways. And we do not really think about that much about all this being in cosmology. But yeah, anyway, thanks for the exposition, and I invite Ajahn Kampi to give to Avik a small token of appreciation.
I go there. Oh, I go there. Oh, no, fine. Oh, okay.
Oh, thank you for visiting us and nice talks, as well as peaceful collaboration.
Thank you.